Okay, so today we have Professor Weitao as our first lecturer, so for the sessions. And Professor Weitao, sorry that this is in Korean for Weitao, but then I guess it's better for our students and other audiences. So as you may know that in 2015, according to Nature's, dense functional theory was related as like one of the main the research fields in the history of humankind. To be precise, out of 100 paper, there were like almost 12 papers from DFT field, and actually out of 10, top 10. So this is about, we are talking about all the paper published in human history. Okay, so out of top 10, there were 2 papers from our field, first principle calculation, namely DFT. And Professor Weitao is actually one of the authors of this paper. So he did a really great contribution in the sense that for Professor Walter Kohn got the Nobel Prize in chemistry, although he was actually a physicist. So so now I guess if you didn't know Professor Weitao, you more or less understood how important his contribution was in our field. Okay, so without further ado, yes, I should let Weitao give a invited talk, lecture actually, for 2 hours today. So we really appreciate your participation and these lectures. Yeah, please go ahead, Weitao.
Okay, thank you. So I need to share my screen now.
I think you probably able to share again. Should I let you
share the screen?
Okay.
And I don't know which one to share now. So let me try to. Oh yeah, now I see. Okay.
Do I need to do anything to let Weitao?
I'm trying to share my screen to see if it's right.
Oh, okay. Yeah. Now, yeah, we see your screen. Yeah.
So is that right now? Correct.
Yes. Please go ahead. Yeah. Yeah.
Okay. Now, can you see my screen?
Yes. We just switch to the other
screen.
Screen. Yeah. Yeah.
That's
you
the
can
problem.
swap the display settings.
Okay. How about now?
Yeah, perfect. Please go ahead.
Okay. All right. Thank you. Thank you, Yong-Hoon, and then thank you, Yong-Woo, for the invitation to give this lecture. And it's my great honor to be here with lots of young people to be in the school. So really, I enjoy interaction with school students, with audience, and it's maybe in the future, I hope to be able to give the lecture in person and we'll be able to see you and interact with you. So from what I understand, there's already a good DFT lecture and a good lecture on TDDFT on the fundamentals. So my focus on my talk will be understanding the approximation that we use in DFT, what are the existing systematic errors, and how can we overcome those errors. And I will divide my talk into the 3 parts. The first will be very, very brief. That's the fundamental principle and the approximation in a very, very brief manner. And then it will tell you the our understanding of what are the systematic errors, and how can we understand it from very fundamental quantum mechanics. And then the second part of my talk will be how to overcome the systematic errors. So we know what we are interested in is the ground state or the excited state of the Schrodinger equations. So it is a really complicated problem for many electrons with electron Yong-Hoon, can you see my cursor? Can you see my cursor?
We see your cursor.
Oh, okay, wonderful. Thank you. So this two electron operator is more complicated things, and then the wave function description of many electron problem has to include all the electrons. And the challenge is that the equation is really simple. It's the linear eigenvalue problem, but the variable is very complicated. The wave function depends on every coordinates, every electron. And for one electron, you will have 10 to the 3 description because it's 3-dimensional 3D coordinate. For 2 electrons, you have 10 to the 6. And for n electron, you have 10 to the n, 3n. So this is really the exponential growth of variables. So describing many body with this incredible details is really a huge challenge. And that's the exponential dependence in terms of number of particles. This is called the curse of dimensionality, and this problem is caused by the extra dimension in the mathematical space. Adding one particle, you add 3-dimensional to the problems, and that's the really a nature of partial differential equation. So where is this exponential growth of information? Actually, it's in the description of wave function. To start with, to completely specify a molecule or a material, all you need is the number of particles and the position and type of atoms. And that's really simple. So this information is completely described by n, the number of electrons, and v of r. This is the external potential that describes the nuclear interaction with the electrons. So this is the Coulomb potential. So these two variables completely specify this information and specify the Hamiltonian. So the Hamiltonian, and then once we want to solve the problem, we get the wave function. That's where the exponential growth of information. The Hamiltonian is very compact, but the wave function has this exponential dependence. So this potential, this V, is a electrostatic potential from the nuclei. It's the sum of all the contribution from the nuclei attraction. And so instead of wave function to describe the quantum mechanics of many electrons, is it possible to use a much reduced variable? This is the question here. That is, in terms of information content, is similar to the particle number and then the potential, the electrostatic potential. And indeed, that is possible, and that is the electron density. So electron density is 3-dimensional information, and it is you integrate over, it gives you particle number, and it has the same information as the number of as the electrostatic potentials. So and furthermore, you can describe electron density of any molecule, any material with computer, and also it is observable, and that's make it very attractive. And but of course, the most important is the following information, the following theory that's developed by Walter Kohn and Pierre Homberger and Lu Shen. So this work that was laid down in 64 and 65 lead to the Nobel Prize for Walter Kohn in 1998 chemistry. So what proved in the principle in this DFT principle is that the number of electron, the electron density completely equivalent to the potential and electron number. That information is one-to-one mapping, and since the particle number and the wave function and the electrostatic potential determine the Hamiltonian, of course they determine the wave function, but without that complexity of the exponential dependence on particle number. So that's really the very, very elegant and deep, very profound theory. The second part of the theorem developed by Kohn and Shen is that the electron density can be expressed as the orbital density square. And this is like the orbital does not have the meaning of a wave function, but it is an effective wave function for the electron, for a non-interacting electron systems. So this is really a remarkable machinery, so that the computation of DFT for the electron density can be done on the orbital level. So with the fundamental theorem proof, I mean, I'm sure you heard this in the DFT fundamental lecture, the only thing that's left unknown is the exchange correlation energy. So the energy can be expressed as kinetic energy, potential energy, Coulomb interaction energy, and exchange correlation. And exchange correlation is a small part of the energy, and it's the only unknown piece in the energy. For an atom, it is about 10% of the total energy. So we'll be making approximation on the 10% of the total energy. And the approximation, what approximation are available? So the first approximation that developed in the original work of Kohn and Shen was called local density approximation. And this approximation was good for many things, but not quantitative enough for many things. So it was very powerful, but not quantitative enough. And the much better theoretical development in terms of approximation to this exchange correlation energy was developed in the 80s to the 90s. And that's come from the three laboratories from Axel Becker, Bob Parr, and John Purdue's lab. And this, so Yong-Hoon mentioned the Liang Parr functional. That was when I was working with Bob Parr, that we developed that. So this type of development leads to what is called generalized gradient approximation, and then hybrid functionals. So then they make the accuracy to much more quantitative. The prediction can be more reliable and much better than other wave function approaches. Of course, there are much more accurate wave function approach, but then you have to pay a lot more price in terms of computational cost. So density functional theory with those approximations has been really widely applied to determine the structure of matter, the atoms, molecule, nano, condensed matters. So it's really broadly applied for chemistry, physics, biology, engineering, and has been used to study chemical and biological functions and electronic property, vibrational, magnetic, and optical properties. So there's really very, very broad applications. Let's look at the approximation that what is in a little bit more details. So the approximation, the LDA, local density approximation, is a electron density times the exchange correlation energy per particle of a homogeneous electron gas of density rho. So this was the first approximation, and that developed by Kohn and Shen. And the exchange part of this LDA was developed much earlier. We call the Dirac exchange energy functional. It's very simple form. This approximation is very simple, but it's not accurate enough. The later approximation would, let's say GGA, would include the gradient of the electron density, and then the hybrid would including some exchange from Hartree-Fock or from Hartree-Fock exchange operator or exchange energy, and some combination of Hartree-Fock with GGA. And then there are other range separate functionals. So there are lots of other developments, but lots of quite accurate readout, or in terms of broad application, is still on the GGA and hybrid functionals. Many applications. So these are really successful story. But what I want to focus on in my talk is not about the success. It's about the failure of the existing approximations. So in principle, DFT is exact and should give agreement with experiment or any high-level wave function calculation in all situations. And indeed, approximate functional perform very well in many systems, but it can fail dramatically in other situations. And these other situations are not uncommon. You can see them in many cases. And this is not the failure of the principle of DFT, but it is the error in the approximation we make. So it is the error of approximation. We don't know exact functional form. We make approximation, and in that approximation, we have introduced errors. And what is really interesting to us was that we were able to understand this error in this exhibit in a very different way, but we were able to trace to the understanding that they come from the same origin. So it's systematic, have the same common mathematical origin, and that is why we spend lots of time to try to understand the issue and try to since we can understand it, then it provides a way to move forward to improve it. So what are the problems? This is the first set of problem that exists in the literature, and this I have the list here. So for example, the first one, if you take the dissociation limit of a molecule or molecular ions, your answer is always wrong with your regular DFT calculation. For example, a molecule dissociation, the dissociation limit should be neutral atom, neutral species. It should not be charged. And DFT calculation always give you a fractionally charged systems. It's not integer, not neutral, not integer. It has a fractional charge. And if you calculate reaction barrier, the chemical reaction barrier that from ground state to the product, it goes to a barrier. This barrier always underestimate reaction barrier. And if you look at band gap of material, it's always too small. So you always predict a smaller band gap than experimental observation. So this behavior, they look very different. They look like mistake in a very different way, but through our analysis, we are able to understand this through this analysis called fractional charges, and I will introduce to you. Through this analysis, we are able to trace this. They have all have the common mathematical origin of this is called delocalization error, and I will introduce that. So to understand this, the simplest example is take the simplest molecule in the world, H2 plus, hydrogen 2 proton with 1 electron. So this is one electronic problem, and it should be really simple to solve in wave function. Yes, indeed. So Hartree-Fock theory is exact. This Hartree-Fock result is exact curve. But if you apply DFT, different DFT, say the GGA or the hybrid functional, you get very good result or good result near equilibrium. So you have good description of bond length and bond energy. But when you stretch the molecule to a large distance, at a very large distance, you can see the answers are so wrong. The energy are completely wrong. Basically, this is qualitative failure of the density functional calculation. This, you cannot rely on this set of calculation because it's so far off compared to the exact answer. And we know it's wrong at a large distance, but even at small distance, at like say 2 or 3 angstrom, you're still seeing the error. You're seeing huge error. So this was really puzzling, and then was dramatic failure. And so you can look at this paper over 20 years ago, 1998. So we look at this phenomenon over 20 years ago with my former student, Yin Kai-Jiang. He's now a professor at NYU. So we look at this and then we thought, okay, so this was, you're getting fractional charge. You get, instead of 1 electron, you get your energy is too low for this systems. And it was, so that was our first attention to this. And it took quite a while for us to fully understood what happened. And what happened was, so many years later, quite several years later, we understand it in a very different way, and in a really that's the path for the much deeper understanding. So what was in the literature available already in 1982 was the result from Perdue-Parr-Levy modules on this called PPLB result for DFT for fractional number of electrons from grand canonical ensemble at 0 temperature. So 0 temperature, then energy is a variable, and being grand canonical ensemble, your molecule is in equilibrium with a reservoir of electrons. So your particle number fluctuates and can be non-integer. So this non-integer and the average number can be a non-integer. And what they have proved was that the energy for this fractional number of electrons is a straight line between n and n plus 1. It's just a linear interpolation. So this was remarkable result that they proved that when a finite system in an equilibrium with a reservoir at 0 temperature, that's the result. So this was exact result. And what we later realized in 2000, year 2000, what we realized was that actually the result is not, the grand canonical ensemble is not really directly applicable to the system we are talking about. We never have a reservoir of electrons. We only have a finite systems. So the fractional information is really interesting, but not directly relevant. And what is this different perspective that lead to the exactly same result was what our contribution in 2000. So this different perspective, it comes from this following this slide on the thing. It's the quantum mechanics of degeneracy. So what is that? Is that the wave function for a degenerate state, you have 2 wave functions give you same energy. Okay, then any linear combination of wave function give you a solution, the same solution, and the same energy with different solutions. So you have freedom in terms of your wave function. Okay, so this is quantum mechanics. Basically, really simple. It's saying Schrödinger equation is linear. Okay, but now if we remember the fundamental principle of DFT, say density can replace the wave function as a basic variable. So, but how you are going to take this information? What is this degeneracy principle reflect in the electron density? You have reflected in the wave function in this form, but in density it's unknown. And that was So we come to the conclusion about that in 1 minute. So let's do this analysis for H2 plus at dissociation limit. And at the dissociation limit, you have a proton and another proton, electron stay at B. That's one solution. Of course, you can have a degenerate solution, electron at proton A and proton B has no electrons. So these two are degenerate solutions. So I can combine the two degenerate wave functions anywhere I want to be a degenerate solution. So I take the average, take this alpha and beta and take the average, normalize it. Then I should have a wave function that have the same energy, right? Okay, so if you look at this way, it's not too interesting because that's absolutely true. But if you look at the electron density consequence, something amazing happened. In this gamma state, which is the average of alpha and beta, you have half electron in A and half electron in B. And A and B are separate by infinity. So they are stretched to infinity. So they don't have interaction. These are the completely separated systems. So half electron and another half electron are walled away. And so being two systems, energy, they should be independent. So you should be, this define actually half electrons. This analysis define half electrons. So half electron is defined as this object because the other half is infinity far away, non-interacting. So this half electron is the same as this half electron. So the energy, not only we define the system with half electrons, but also we define the energy because this energy together has to be the same as the other energy. So energy of half electron must be half of energy one electron. And this is exactly the curve here. So energy one, no electron and one electron, and half electron is in the middle. It's just halfway of the one electron energy. So this is the linear line, the middle point in the linear line. So this discussion that leads to this conclusion is completely based on the degeneracy principle in quantum mechanics. So fractional electron arise as a way the electron density encode the degeneracy information. So now we define this, and then of course I can use the same argument to in the paper, our 2000 paper, we extended it to describe any number of electrons and any fraction. So you can define, you can prove this for the entire curve, and you can prove this curve for any number of electrons as well. And so for the students, I have a exercise challenge. If I wanted to get a point 1/3 of electron here at this point, how do I design my systems? How do I design my proton and charge so that I can prove this linearity condition at 1/3 of electron? So 1/3 will be 1/3 of this right here. Okay, you try to prove this point. All right, so this is the exact condition. So this exact condition, this linear condition, is really how degeneracy quantum mechanics expressed in terms of electron density. It's not so much about equilibrium with the electron reservoir. That's one perspective. The result is identical, but from the degeneracy perspective, then it's a lot more relevant because it tells you whether your functional is treat the situation, degenerate situation, correct or not, right? So if your functional deviated from this line, means that it's treating some degenerate conclusion that is the energy that is different from the right answer. And our exact functional should be this black straight line. Typical LDA, GGA, and even hybrid functional, typical all your DFT functional behave convex. It doesn't behave. It has better solution approximation near the integer, and it has really a large error at half point here. The error is very large at the middle point, and at integer it's much better.
Professor?
Yes.
I cannot see your cursor. Could you?
Oh, you cannot see my cursor. So can you see the cursor of this time?
Now I
oh,
can see.
Sorry. I pointed on the wrong screen. Yeah.
Now I can see.
Yeah. Okay. So now you can see the cursor. Yeah.
Yes.
So the integer point is much better approximation, but the middle point is really the challenge, the significant error. So our approximate functional means deviate from the exact condition. What it means is that the degenerate solution of the Schrödinger equation and the approximate functional don't give you the same energy and give you this state with much lower energy than this than the other state. Okay, so then if we can think about what this degeneracy, this error, this convex error will do, is the following. If you take two systems, just like two protons or two neutral molecule, any kind, and add the electron, these two are not interacting separate to infinity. You add the electrons and ask the question, where will the electron go? Where the electron should be one molecule, the other, or spread out? Of course, because these two molecules are non-interacting, the answer is that they are all the same, different electron in one or the other or spread out the same energy. That should be the degenerate quantum mechanical result. However, if your curve, E versus N curve, is convex, then you have this inequality. So energy of half electron times 2 is less than the integer, right? So the answer will be always spread out. Electron will share between the two species, and that's energy is lower. But this inequality is wrong. It should be equality, to be equal. And when it's equal, then it's straight line, and less sign means it's convex. So then the conclusion is that the electron will try to delocalize for mistake of the energy functional, not because of the physics. So then if you look, there's another type of functional that behave approximation that give you concave. That's Hartree-Fock. The Hartree-Fock approximation is very different from DFT approximation. It's the green curve behavior, concave. And when you have concave, then the opposite result will happen, is that the energy will always localize. And so you have a different kind of error. So basically the delocalization or localization error are the mistake in the approximate functional systematically, because the answers, while the answers should be degenerate, you should not have preference, but the approximation failed to do that. So we call this delocalization error. It's convex behavior, and the top line called localization error. And the consequence for delocalization error, that's for all the functional, will predict too low energy for delocalized distributions, and then it will give two delocalized distribution when it's possible. So if your calculation allow your electron to delocalize, then system will delocalize to lower the energy. Here is the curve for dissociation of H2 plus. So the dissociation limit here is exactly matching the half electron error. So the delocalization error is exactly capturing the dissociation limit. And that's mathematical analysis is at infinity. So you can think about this as asymptotic mathematics at dissociation limit. And so the error at infinity actually it's really significant for finite distance. So that's the so now we can, with this fractional charge tool, we can understand all this behavior of functional that has wrong behavior as the delocalization error, all of this. So for example, let's look at transition state energy. And I will say a lot more about band gap in a minute. But transition state energy is the case where electron is delocalized between the two chemical bonds. One is being broken and one is being formed. Compared to the ground state or the product state, the electron localized in a bond. So the transition state has a situation where electron is more delocalized than the ground state. And therefore, the delocalization error will give you a lower energy systematically compared to what it should be. And that's the underestimate of transition state energy. You can also see if your calculation allow the charge to delocalize, it will spread out and it will make mistake. So let's look at a calculation for chloride in water. And this in water cluster or water bulk will be similar. And if we ask the question, where is the negative charge of chlorine? Where is the negative charge? Of course, the physics should be that the negative charge stay with the chlorine atom. But in an LDA calculation, if you look at the negative charge, it's not in the chlorine atom. It's in every water molecule grab a tiny bit of charge. And because this is a happy lower energy, of course, it's the mistake of the functional. It has nothing to do with physics. And that there's really this very severe problem. If you want to do simulation, the electron density is wrong and the energy will be wrong. I want to also make a comparison with a concept that appeared earlier. And I don't know if this was covered in the DFT talk, the basic principle DFT talk. But there was a concept called self-inflection error. It was introduced by Perdue and Zonger in '82. And it's basically for one electron system, the exchange correlation energy should cancel exactly the Coulomb because there's no inflection energy. But that cancellation was not complete. And it's the self-inflection error. So this self-inflection error is, you can do the correction for every orbitals, and that's the self-inflection error corrections. And for lots of calculation for molecule, the general self-inflection error correction really doesn't improve. So was puzzled for a long time. But before our work, before 2006, the field of DFT, or many people at least, including us, believed that self-inflection error was the source of the systematic error in DFT. And but our understanding completely changed in 2006. So this was before our delocalization error concept. So what happened was in 2006, there were two self-inflection error-free functional that designed to be completely free of self-inflection, perfect for any one electron systems. So this was Becker's Becker functional 06 and MCY. MCY is from my lab, from Maurice Sanchez, Cohen, and myself in 2006. So these two functional have very different form, construct very differently, but behave very similar. It all had no self-inflection error, but it has. So we were very excited when we developed it, and then want to test out against the set of errors. and then we see every one of them almost. The error don't go away because of the self-inflection connection. So that was a serious wake-up call that, well, it shouldn't be, this self-inflection error was not the reason for the systematic error. And then later on, we call this many electron self-inflection error, but was used in 2006 in our paper. But it was also confusingly introduced in a different paper by Purdue and his collaborator. They describe any, also including Hartree-Fock problem. So this delocalization error that was named in 2008 really capture the mathematical origin. It's the physical feature of this error. So we now call this delocalization error. So there is also a very interesting dependence on size-dependent manifestation in the self-inflection error. So this is the scenario for small number of atoms and small physical extent. So the integer number energy at integer is good accuracy, and that's the curve I draw. The energy at En is good. Fractional is poor because it convex deviation from the linear conditions. Okay, but if you have large number of atoms and bulk systems, the story changed. The integer number of electrons is poor accuracy for charged systems. It's good for the neutral one, but poor for the added electron or taking electron away. And fractional actually it automatically satisfies the linear condition. So the fractional is not a good indicator anymore for bulk systems or for a very large number of electrons. For finite number of atoms, but with a large physical extent, means dissociation limit of finite systems, then the integer is error for charged systems, and the fractional is error, is convex deviation. So it has both. So this was really, it took quite a lot of challenge for us to understood this, and this was summarized in this paper 2008. So these are the first systematic error. When we talk about fractional number of electrons, there is also a very interesting concept called chemical potentials. And this concept is associated with the changing particle number, the energy change. This is exactly the thermodynamic definition at zero temperature. Energy derivative with respect to particle number when the potential is fixed. That's chemical potential. So from the PPLB condition, which is exact, then the chemical potential will give you ionization energy or electron affinity, because it will tell you the difference between N and N-1 or N+1 and N, depending on which side you take the chemical potential. There are two chemical potentials because it's discontinuous, derivative discontinuous. So then means that if we can calculate the chemical potential, then we know the information about ionization energy and electron affinity. And that's a really important quantity for band gap, because band gap is the difference between the N+1 and N-1 slope. So it's I-A. This is experimental definition for fundamental gap. And if you can calculate the I and A from the derivatives, then we call this derivative gap. So you can calculate the derivative, the chemical potential, then you get the gap information directly. Of course, they agree only if this is linear, if N plus delta, the fractional is linear. And for our, so how do we calculate the chemical potential? That was not known until 2008 in our paper. So chemical potential is important, but you don't want to calculate N and N-1. You want to calculate directly from the ground state calculation at the end, because adding electron or minus attaching electron for finite system you can do, But for bulk, you cannot do easily. So what do we know about the meaning of orbital energy? This relates to chemical potential in one more. The orbital energy in the CONSEM, the orbital energy in CONSEM is the Ionic theorem that was developed really earlier. The energy, the orbital energy is the derivative of energy with respect to occupation number. And that's what's the Ionic theorem. And then there's another thing we know about the eigenvalue. It's the asymptotic behavior of electron density and the CONSEM effective potential. If you have the exact CONSEM hormone, then the hormone energy is the chemical potential A equal minus I. So this is assuming you have the exact density, the exact hormone should behave in this way. So, but this conclusion is only for finite systems. And also that the exact CONSEM potential is the potential deliver the exact density, but not necessarily the functional derivative of the exact exchange correlation functional. No, there's no connection to that because actually the exact functional is not differentiable. And well, I will show in one moment. So the potential actually, if you would thinking the potential as a quantity that map to density, is not defined up to a constant. So there's this complication. So what we proved in 2008 was the following: that if you calculate chemical potential, giving a CONSEM calculation, how do you calculate exactly the chemical potential? Derivative with respect to particle number is given by the eigenvalue of CONSEM or generalized CONSEM. Okay, and this including adding electron, then will be the LUMO, and taking electron away will be HOMO. So it's a HOMO eigenvalue or the LUMO eigenvalue. So before this work, there was some discussion about HOMO, but there was never any understanding of what is the meaning of the LUMO orbital energy in CONSEM. But from our work, we derive it. I'm not going to detail how the derivation is. Detail is in this paper. Is that the chemical potential defined in this way is related to the eigenvalue, and it's exactly the eigenvalue, and it doesn't depend on whether your functional is exact or not, as long as your functional is differentiable. So you can differentiate the functional exchange correlation functional with respect to density or with respect to density matrix. That's the answer. So this chemical potential is associated with a density functional approximation. And that's really, so you can now understand the eigenvalue is the chemical potential associated with the approximate functional we use. So this actually gives a very interesting interpretation for Hartree-Fock theory. So if we take Hartree-Fock as a density functional approximation, then the frontier eigenvalue of the Hartree-Fock theory, the HOMO and the LUMO, of course, we have the Koopman theory, which is saying that the HOMO energy should be the ionization energy, the LUMO should be electron affinity with the frozen orbital approximation. Right? That's the Koopman theory. But in here, we are saying that the HOMO is the chemical potential of the Hartree-Fock theory, taking electron away, and the LUMO is the chemical potential of adding electron. So it is a very different interpretation. Of course, you can use this to approximate ionization energy and electron affinity, but the physical meaning is the chemical potential. Okay. So HOMO energy is the chemical potential for electron removal. LUMO energy is chemical potential for electron addition, and fundamental gap predicted from DFT with CONSEM or generalized CONSEM calculation as the CONSEM gap or the generalized CONSEM gap. And then, for orbital functional, if you do OEP calculation, then the OEP gap is not the chemical potential prediction. It's a different story. So one cannot use OEP calculation gap to connect to experimental gap. So if you're functional, now we understand how to calculate the chemical potential, which is the slope. And if your functional is convex, then your slope will underestimate experimental ionization energy, I, and it will overestimate the electron affinity. So the I minus A will be too small when you have a convex curve. So the gap will underestimate the gap. And then if you have a different functional like Hartree-Fock, the story is opposite. And I minus A prediction will be too large. So this really analysis capture all the observation of band gap prediction with Hartree-Fock and with density functional approximations. Underestimate the gap, Hartree-Fock overestimate gap for atom, molecule, and bulk. So the fundamental gap can be predicted only if the functional have minimal delocalization error. That's the conclusion. We know how to predict it, and only accurate if you have minimal delocalization error.
Weitao,
yeah.
Before going forward, for our students, maybe you can make some comments about the difference between Kuhn-Sham and original Kuhn-Sham and generalized Kuhn-Sham scheme.
Very good. Yeah, let me go back to this. I think I have an equation. Let me see if I can. No, maybe.
I think you just show some equation where you mentioned your PRB paper from 2008. So maybe you can just use that equation maybe.
Okay, this equation. Yeah. Okay. So constant, the constant calculation is when you have kinetic energy operator, the external potential, the Coulomb potential, and the exchange correlation potential. So if the exchange correlation potential written in this form is the generalized constant, that means this looks like Hartree-Fock operator. This is the Coulomb, which is local. This is the exchange operator. Then you'll be exactly like Hartree-Fock. As generalized constant is the interpretation of Hartree-Fock in DFT language. But of course, it's not limited to Hartree-Fock. You can have a functional that depends on density matrix, and taking the functional derivative with respect to density matrix, you live with a potential that is non-local, R and R prime. And this non-local behavior in the exchange correlation potential is what we call generalized constant. So let me, then if it is local, if your functional only depends on density, this will be a local function and then a delta function in R and R prime. So that will be local, that will be the constant. So actually, generalized constant was already in the constant paper. In the original constant paper, it has the constant and generalized constant. And it was also in earlier days when people try to add a correlation energy to the Hartree-Fock, and then the equation become like Hartree-Fock plus a local potential. So it's already used in that way. And this was somehow viewed as not the pure DFT because it depends on density matrix. So there was a lot of effort in the field to develop what is called OEP, optimized effective potential, to replace this non-local potential with a local potential. But you can do that, and numerically you get exactly nearly the same energy, no physical difference, except the orbital energy will be different. The orbital energy will be significantly different. The electron density will be very similar, but orbital energy will be significantly different. And in those scenarios, only the generalized constant is related to the chemical potential. The OEP eigenvalue are not related to the constant potential. directly. So you cannot use the OEP gap to connect to experimental gap.
Okay, thank you.
Yeah. Okay. So let me go to the second errors that sorry. Yeah. So I will introduce the second set of errors, and then we'll take a break. So the second set of error is the what I call this also about degeneracy. It's again about degeneracy, but this type of degeneracy is different from the other degeneracy we talk about. We will see in one moment. So the if you dissociate a covalent chemical bond, you have a very large error in the asymptotic. Again, also at the asymptotic, and the energy will be too high, except if you break the symmetry, do a broken symmetry calculation, which you can do sometimes, but not always. You can do a broken symmetry calculation in some scenario to get energy correct, but wrong electron density, wrong spin density. But this is not a solution you can use all the time, because you only have two density, alpha and beta, to break. But if you dissociate the molecule in many ways, you cannot do any trick at all. So basically, dissociation limit has a large error. Transition metal systems has error, significant error, and these are all related to this what we call in physics called the strongly correlated systems. System with strong correlation. We'll come to in a minute. What is that? And most dramatic example is more insulator, and it is an insulator. But if you calculate the gap from any DFT calculation, you get the metal. You don't get the gap. You never get a gap in principle. So this is the issue of degeneracy and near degeneracy. And the tool to analyze this is what we call fractional spins. And it is the static correlation error or strong correlation error. So static correlation is what term used in chemistry more frequently. Strong correlation is more used in physics, but the same thing. So what happened is that when you dissociate a H2 molecule, one more electron in your systems, you Hartree Fock now, this red line has a very large error. The correct answer should be 0. And different DFT has a different error. They're all very significant in this error. We can do the same analysis, this degeneracy principle. But now we can understand this degeneracy are different than the previous case. But it's all about degeneracy. So at the dissociation limit of H2 molecule, you have a proton with one electron and another proton with another electron separated by infinity. So this is the proton with electron spin down, and this will be spin up. That's one state. Or you can flip the space, and then your proton A will be with electron up, and proton B with electron down. These two are degenerate solutions. I can linearly combine it and then get a state that is same energy. And if I look at the wave function, not too interesting, but if we look at the charge distribution or the spin density, it is very interesting. It has this species here with proton A has two half electrons. One half is spin up and one half spin down. And that's exactly what we call the fractional spins. Electron number is integer, but fraction spin is fractional. So this another object with proton B is identical. So these two, again, I do the same analysis, and then the non-interacting principle or the size consistency principle. The answer for this energy, I define the fractional spin object, and the energy should be the same as spin up or spin down, right? And in fact, actually, not only the up and down and the middle one is same energy, but you can be any of the spin polarization, the same energy. And that can be proved also in the paper, in this paper in 2008. So you can, this principle was actually described earlier in our 2000 paper, but we didn't realize how important it was until 8 years later that connect to the strong correlation problem. So this dissociation limit of H2 is related to the failure of functional to describe this degeneracy of this fractional spin object with spin up and spin down. The energy is too high for this state, while it should be the same, but it failed. So the fractional charge and fractional spin are manifestation of quantum degeneracy in classical variables, density and spin density, basically. And if you stay with wave function as your basic variable, this was never a problem, always integer. But the moment you reduce variable, use electron density or Green's function or density matrix, then the degeneracy principle reflect in the fractional charge and fractional spins. So this is how that is our discovery that this classical variable reflect the quantum mechanical degeneracy in the wave function, and that's what do we know so far? We know the fractional charge condition from Purdue, Levy, Baudius, this 1982 paper. So fractional spin condition was derived in my lab, and in 2009 we were able to combine these two to define the fractional charge and spin together. So you can mix all the different degeneracy, and then the conclusion is really very interesting. So first, the fractional spin conclusion is that remember linear combination of degenerate wave function give you the same energy. Here in this 2000 paper, we prove that linear combination of degenerate electron density give you the same energy. That's the underlying the fractional spin. So this is very dramatic because linear combination of wave function is not the same thing as linear combination of electron density. But what we saw is that linear combination of degenerate electron density give you the same energy. And then you can, this degeneracy is happen in the same space. But when you degenerate with another part of space, that introduces the particle number change. So this can be combined, the fractional charge and spin can be combined and leads to this condition called what we call the flat plane condition, because now it's two variable, the charge and spin contain. And this more complicated was also proven exactly. And this condition actually leads to a very, very dramatic conclusion that the exact exchange correlation functional cannot be an explicit and differentiable functional of the electron density or the density matrix, either local or non-local. So we just proved that the functional cannot be, if you express a functional as density or density matrix, it cannot be a continuous functional, because we will find an example where this will lead to wrong physical result. So, and that's the conclusion. And of course, most of the approximations are continuous functional, so we don't have the exact functional. The manifestation in a to show this fractional charge and spin condition combined is the following picture. So if you take a hydrogen atom, take one electron away, you have a proton. Add one electron, we have an electron spin down, spin up, and then two electrons, H minus. So in a so this is the four corner on the spin occupation. The normal wave function will only have this four corner as your answer. That's it. That's it. You use a wave function as variable. But if you use electron density as your variables, every point continuously on this intercepting this plane is a possible physical state, a degenerate situation. And then the energy is, it will prove it's this the two planes intersecting each other. So the quantum mechanics is much richer in the density variable. And you have to, your approximate functional have to satisfy this flat plane intersecting condition. And if it fails, it will fail to describe physical systems. And in particular, this blue line here is and it is derivatively discontinuous. It's continuous, but have two different slopes at this middle point. This discontinuity is the necessary condition to describe the more insulated gap. And our approximate functional from Hartree-Fock could be GGA hybrid to even RPA fail to describe that discontinuity. So any of this functional applied to more insulator will lead to a metal. And much of the insight that I share with you is summarized in this paper, already 10 years old. And so this ended my first part of the talk. And in the second part of the talk, I will tell the story about how we use the understanding to make improvement in the functional. Okay, so I will happy to take question now. Yeah.
So to take some several minutes of break, maybe a short question, please. If there is anyone who would like to ask any questions. Okay, so we are behind the schedule a little bit, so maybe we can just take some short break and then.
Okay.
And then
I have a.
Oh yeah, sure. Please go ahead, Professor. Yeah.
Thank you very much for the very nice lectures that that will be helpful for a lot for the students. Then I have one question that that kind of auxiliary functional, so-called Hubbard functional to
correct
make the linearized. Could you comment that it?
Very good. So you are talking about the DFT plus U.
Yes.
Right?
Yeah.
Yeah. So I will make some more discussion on how to correct it. So LDA plus U was an attempt to fix the D-electron problem. Yeah. So it was trying to restore some linearity.
Linearity, right? Yeah. So.
Yeah. But it so it was empirical approach, and then it has quite a bit of application that if you have the right U, you can help to correct the gap. But it's the application in terms of other material is much more limited, and for finite system it's very limited. For organic molecule rather than transition metal, it's very limited. I don't think there was much broad application. But the phenomenon we described, the systematic error, not only for transition metal, but also for any other thing.
Okay.
Well, in some sense, I guess what you are trying to say is that maybe just naming issues. So there are lots of different type of DFT plus U where you maybe can be ab initio way determined to observe this the fractional occupation conditions, right? The linearity conditions. So, for example, actually, Yong here, he has been working on this some years, and then I think his formalism, in some sense, can be included under the umbrella of this generalized condition scheme. So maybe a very restricted DFT plus U might be, as you said, is limited. But then, if you just extend what you are trying to say, I guess maybe DFT plus U can be also included in this umbrella that you probably want to talk about.
Absolutely true. So LDA plus U or DFT plus U can be considered as a way to overcome some of the problems. Yeah, for some systems, for transition metal system in particular.
But my question is, might be also can be formulated in another way. Probably you will talk about this more in the second lecture. So can you you want to say that the generalized cohesion scheme is the way to go for many practical applications?
Yes, yes, I think yes, I think if your functional only depend on density, then you have constant.
Local exchange correlation function is very limited. That's why
then you just
saying, right?
But no, depending on density, it can be non-local. It can be very, very non-local functional density. Then you still take the functional derivative, you get the constant potential, your local potential. However, we know the following thing, that even if you have the best how to say, if your constant exact constant potential, imagine if you have a ideal constant of function of density and then take the functional non-local energy in terms of density, but the potential is still local. If you have the ideal dream one, you still will be failing to describe the band gap, because that potential describes the correct density. We can invert it, get it the density, but the gap is still very off compared to experimental gap for semiconductor or insulator. So what does that mean? Is that the functional cannot be a numerically continuous differentiable functional of density. So writing a functional as a compact form, however complicated a functional of density, explicit, that you can take the functional derivative to get the potential, that is not a functional that you want. Yes, it failed to describe the gap for semiconductor. Okay.
Okay.
So you have much better chance of getting a functional that in terms of density matrix and constant, generalized constant, leads to the non-local potential. That would be the generalized constant. But that is also not enough, because that's not enough for strongly correlated system for more insulator, because as I point out in one of the slides, the exact functional cannot be a explicit differentiable functional of density or density matrix. But the functional density matrix is much better than the function of density, but still not enough. So that's
maybe we can talk about this a little more in the next lecture. After, thank you so much. Short break.
Great.
Okay. So maybe you want to please so take some break, everyone, and we will be back in maybe let's say 5 minutes.
Okay.
It's already 16, 17. So So I guess we are behind the schedule. So everyone, let's meet again at 22:03. Yeah. Okay. See you.
Okay. Thank you.
Let's begin the second lecture. So Professor Weitao, Weitao, would you get started?
Okay.
Thank you.
Yeah. All right. Thank you for coming back. So I wanted to describe the challenge to overcome the problem. So come back to this this simple problem, H2 plus dissociation. If we look at the dissociation curve at energy of as function of distance, so DFT behave quite reasonable at equilibrium and fail very badly at last distance. So that's the error we want to correct. And we know this at the dissociation error is limited. It's the error is the delocalization error. The energy for half electron too low, and that's the issue, right? So the challenge is well, we want to correct it. So if we look at this right-hand side picture, look, that's not that hard to do. It's look like a very much like a quadratic curve. All you need to do is to make the quadratic linear, right? But this quadratic curve is in terms of a variable that's called fractional charge, fractional number of electrons. Well, the fractional charge, fractional number of electron does not exist in any finite distance. It exists only at the infinite separation. When you go to infinity, we can talk about fractional. But at finite distance, you always have one electron. It is your system is finite and one electron. So that's the challenge. The second challenge is that the correction want to have a last distance, but not at equilibrium. So that's the second challenge. How can you design a correction so that it does the correction, the energy corrected at last distance, but not at small distance? So the question is, what's the difference between the electronic structure at small r and large r? So this was really taking quite an effort for us to understand and to use it, because we cannot use the nuclear coordinate as our parameter in the functional. That would be useless. That would be a functional that we cannot use for anything, right? But we want to use electronic information. So the key to recognize this was at infinite separation. Actually, compared to equilibrium. Equilibrium, you have a chemical bond. You have bonding and anti-bonding. So two atomic orbitals make a chemical bond, split the level, bonding and anti-bonding. So you have a gap. There's a finite gap. But when you separate to infinity, this gap disappears. These two atomic orbitals is your answer, and they are degenerate. So gap of the systems is the difference. You have a large gap and no gap. So the electronic structure is the gap that we can use. So it took us, this is in 2008 to realize this final form that we are using the correction. But before this, there was two previous paper, PIL paper, that we developed. And it has a component of it, but not quite the complete story. So only until 2018, we have more or less the complete story for this problem, for the delocalization error. And this method is called localized orbital scaling correction, LOSC. So we have to introduce a new object called orbitals. It's normal localized orbital to represent the density matrix. And that's really the most innovative part that allow us to capture the fractional charge information and to distinguish between the equilibrium and last distance. And with this allow us to capture the dissociation of molecule band gap for molecule and polymers, and describing spectrum. I will talk about that. So so in the revised version in 2020, we have made it even better. So this is essentially the same, but a little bit better. So I'm talking about this version of the theory. So what is orbitals? It's a linear combination of the canonical orbital, the block orbital or the canonical constant orbitals, unitary transformation. But this unitary transformation is to minimize with respect to a objective function now. So the first is a space localization. This is the adjacent moment of the orbital square. So this is the second moment of the electron distribution. If you have a more localized one, this second moment will be small. And if you have a delocalized orbital, this will be large. So this means localized orbital. And this traditionally is the Boyce localization and in chemistry, and what's used in physics for called maximum localized Vernier function by work from Vanderbilt and Massari. So this is the standard localization object. However, in the orbitals, we add a very interesting second term. This is the energy variance. So a canonical orbital has one orbital energy, precise. There's no energy variance. So this energy variance is when you linearly combine canonical orbital of different energy, then you have a different, if you have an energy change, you have an energy uncertainty. So this is energy uncertainty in the orbitals. And we put a constraint on how much uncertainty you want. So why we do that? Because think about it, we want to combine orbital, and so this localized orbital also sum over all the orbital, occupied and unoccupied. That's very different from traditional localized function or maximum localized Vernier function. They are focused on linear combination of the occupied manifold. But in orbitals, we have to generate fractional occupation. So we have to use unoccupied orbital. So we have use unoccupied orbital, but we limit the energy spread. So if the system has a big gap, like say equilibrium, then the combination of the occupied and unoccupied will take the very large energy variation. So you'll discourage that in this object. And if your orbital is degenerate, then this will localize without paying any cost. So the energy localization will cost nothing. So this is like a benzene molecule. At equilibrium, the orbitals, because equilibrium has a big gap, so you do not include the unoccupied orbitals, and they look like the canonical orbital. So this is very much like canonical orbital for equilibrium. But at large separation, then it becomes mixed with unoccupied orbital, and at very large separation, it looks like atomic orbital. So it's exactly the same object. Through the optimization, it generates different type of orbital. And this orbital, you can see that this set of orbital can tell the difference. This is fully occupied. This is partially occupied. The bottom line, I'm pointing on the wrong screen. So this at one equilibrium distance, these are all fully occupied because the big gap between occupied and unoccupied. So the energy localization will not favor the mixing of unoccupied orbital. At large distance, gap is small. You mix occupied and unoccupied. It looks like atomic orbital. So that's exactly what we want. And so the orbitals span both occupied and virtual space, localized both in physical space and energy space. In contrast, traditional localized orbital is localization in physical space, and you sum over the entire occupied manifold. And canonical orbital only localized in energy space, because precise in energy, but spatially delocalized. So with this localized orbital, this called orbitals, we can make a projection of density matrix and then express the density matrix, exact constant density matrix in the localized orbital representation. So the localized orbital are orthogonal, but the density matrix is not diagonal. So you have the cost term lambda ij in this form. And this allow us to, so for hydrogen molecule at equilibrium, because the gap is large, so HOMO and LUMO do not mix. So there's little missing between the HOMO and LUMO. The canonical orbital is the answer. So you have your occupation 1 and 0. Okay, that's equilibrium. But at large distance, the energy gap is small. So HOMO and LUMO mix, the orbital become orbitals become atomic orbital. So the occupation is half. So with that half occupation, then we can use that information to correct the functional. So that's our correction functional is just add a linear term and take away the quadratic term. So this is the linear term. The chi is the coefficient between I and j, between the two orbital I and j. The lambda ij is the linear term. We add a linear term and minus a quadratic lambda square term. So because the deviation is quadratic, so we minus this. So this is our energy expression with every I and j included. So how do we calculate the kappa ij? So in our earlier work, we already figured out how to approximate this. It's the Coulomb interaction between localized orbital I and j, and then the exchange correlation. So we only put exchange here because this is small part. So we don't have a correlation expression here. And the tau is a parameter which the x is the exact exchange coefficient, but tau is parameter to get the corrected limit for H2 plus. So this is everything in our functional. And with this energy correction, we can add a quadratic correction to the Hamiltonian, to the eigenvalue. The eigenvalue will be derivative of this energy with respect to occupation number. So give you this is the energy orbital energy correction. So let's look at what is the consequence of that correction. So I look at this delocalization error in helium cluster ionization energy calculation. So one helium atom all the way to bulk, but the helium atom are separated by large distance. So this is one helium, 2, 4. So two panel, the upper panel is the eigenvalue HOMO plus the I vertical. So what is I vertical? I vertical is the energy difference between n minus 1 and n in your calculation. So it's just the two integer difference, and this is the slope. So if the curve is straight line, that you will not have error. But the curve is convex, so the HOMO is not related to the, it's a wrong, has a wrong slope. So this error is large, very large, 8 eV, so very, very convex. If you do the hybrid functional, it's 7, so it's still very large. But the vertical energy compared to experiment, this is the vertical energy, the finite difference compared to experiment is the bottom panel. You can see for one helium atom, remarkable. The integer prediction is almost perfect on this scale. It really predicts very well experimental ionization energy by finite difference calculation. Eigenvalue is really bad, but the finite difference is really good. So this is the best part of DFT. Realize that for small system, the integer energy is so good, amazing. But of course, the story changed when you add one more helium. You add one helium that is separate by 20 angstrom, large distance, so that they are not interacting. Then the slope, the eigenvalue prediction versus the finite difference is small. So the convex curve flattened out, but the finite difference is no longer good approximation to experiment. So this bottom panel has error of 4 eV. So 2 helium atom, the ionization finite difference calculation is bad already. But the eigenvalue error is smaller. So you just shift the error from the eigenvalue to the endpoint. But now with LOSC, this is the LOSC correcting LDA, we're able to correct, this result. We're able to correct the eigenvalue and also keep the good accuracy for integer, for small systems. For larger systems, for 2, we do the same thing. We are able to do the same thing. And then this trend persists. When you go to very large number of helium, all the error is, the slope is very good approximation to the finite difference. But the finite difference has all the error compared to experiment. This red, the bottom panel, the finite difference, the charge system for many helium is wrong. It's wrong by 6 eV or 8 eV. And the LOSC correction, we can correct the total energy nicely to this in both scenarios. And so this is the correction for a large set of molecules, 97 molecules. This red result is the LDA ionization energy prediction from the eigenvalue. And this is the electron affinity, underestimate electron affinity, overestimate ionization energy. But LOSC bring these 2 sets of data to the line. Systematic error is corrected. So we eliminate the systematic error.
So I have questions that in your this test, that the G2-1987 test, you use the same tau for all
yes,
tests?
Absolutely. Absolutely. That's 1 tau. Yeah, we didn't change it. Yeah. Okay, so this molecule is a long polyene molecule, and we can calculate for very large finite system, but very large n. The experimental result is in cost in this experimentally known result, and the REST-PT2 is a good multi-reference and then second order perturbation correction. So it has good agreement with experiment, and our LOSC correction also in a good agreement. And we can do for very large systems, and you can see that this will have a finite gap for infinity extrapolation, but LDA will underestimate the gap by quite a lot, and very, very tiny gap when you go to infinity. Same functional, same without changing a parameter. You can look at the task distribution that I highlighted, chlorine in water, right? So chlorine in water, if you do a PBE calculation, the charge on chlorine atom is positive, completely wrong, okay? 0.04, some molecule charge analysis, 0.04, wrong. If you do CCSD, couple cluster, get you minus 0.96. This is about the right answer. And if you do a hybrid functional, you get you minus 0.67. So it's halfway correct. Hybrid functional improve the result significantly. But if you do LOSC on top of PBE, we get much better answer compared to much closer to the correct answer from CCSD. And so now I wanted to tell you we can use exactly the same tool to describe strong correlation with fractional spin. So this is exactly the same analysis, but we have to address the spin, the flat plane condition rather than the linear. So it's more complicated. But we with my postdoc, former postdoc Neil Shu, we are able to divide the functional that dissociates molecule correctly, and this is called fractional spin LOSC. So the fractional, this is, we can look at this flat plane condition. The fractional spin LOSC is able to deliver this two-plane intersecting condition that we made it to satisfy. And that's the reason for dissociation. So N2 dissociation for strongly correlated system, we can describe with fractional charge and fractional spin, then this is corrected compared to LDA. And now it's without breaking the symmetry. Now the eigenvalue. So we have good ionization energy and good electron affinity, but there's more to it. So let's look at the Consem equation and generalized Consem equation. So Consem equation.
Excuse me, I have another question.
Okay.
Sorry
Yes,
to interrupt
please.
you. So
in
your calculation, those orbital, so those
Yes.
optimized orbital, do you use a kind of self-consistent loop? So is energy also changing? So do you have some kind of loop between those two?
Very good question. You raise a very good question. I'll come back to answer that when I talk about the self-consistency, how we achieve good self-consistency. So that was indeed, in principle you have to do all the loop to do the self-consistency, and it's complicated, but we simplified it so that it can be done very effectively. So I'll come back to address that. That was a big challenge for us, how to do proper self-consistent calculation with LOSC. Yeah.
Okay.
So yeah. So this orbital energy. With Consem, you have orbital energy come from a local potential. With generalized Consem, you have the orbital energy come from a non-local potential. But there is also another set of equations in the literature, in the many-body literature, called the quasiparticle equations. And it looks very much like this, except this is self-energy, non-local, but energy dependent. So it's more complicated than any of the Consem and generalized Consem, but it is one electron equation. And this orbital energy here are the quasiparticle energy. It describes ionization energy and the electron affinity, and not only the HOMO and LUMO, but also state below HOMO and state above LUMO. So there are many, the orbital energy is just ionization energy with different excited states. So this is a wonderful theory, but of course it's expensive. And so we already proved the following. The eigenvalue in the Consem or generalized Consem has the meaning of chemical potential, has the meaning of quasiparticle energy for the lowest ionization energy, the lowest ionization energy, and the highest ionization energy, and the lowest LUMO. So for the HOMO and LUMO, we already proved that this eigenvalue are equivalent to the Dyson equation. This is the quasiparticle equation. So then, how about the states that below HOMO and above LUMO? That we know this HOMO LUMO is good. How about state above LUMO? And this good quality of HOMO and LUMO are the following. They are so good compared to GW or different versions of GW for very large set of molecules, 40 molecules. Our result with LOSC or with DFT here, DFT will give you a regular probably 2 or 3 EV error. Our LOSC correction reduced the order error by an order of magnitude to 0.4 to 0.3 EV, and comparable error with GW theory, the quasiparticle equation, trying to solve the quasiparticle equation. Same story with electron affinity. So this good quality of the IP and EA to encourage us to look at the other spectrum. And indeed, we wanted to know what are the rest of the orbital energy. How that compare to the rest of the quasi-particle energy. And the result.
Weitao,
yes.
I also have questions. You mentioned that your orbital rates are actually energy dependent, right?
The orbital leads are linear combination of canonical orbital. So they don't have a fixed energy. They have an energy that is not defined.
But then energy dependence is kind of then in the end embedded.
No, the potentials are, so good question is the equation we have is still generalized constant. So our equation are generalized constant. Our functional are still functional of the density matrix.
Okay, thank you.
Yeah. So we want to look at the rest of eigenvalues. And then we look at here in detail, 3 molecules, very large molecules, and then compare to the, so this is the experimental IP, the lowest, smallest IP, and the LOSC prediction, or the DFT prediction, and the next high IP, they are all good. They are very similar in quality. So the LOSC orbital energy prediction, not only HOMO is good, also the state below HOMO are also good. Okay, and the same story with other molecule. So you can ionize different level, and this orbital energy are good approximation, as good as the HOMO to compare to experimental ionization energy. And that's allow us to calculate photoemission spectrum of molecule, because the orbital energy will be the ionization energy, so you can make photoemission spectrum, and that's the entire spectrum from LOSC calculation compared to experiment and compared to GW. So GW is this last, the middle two, and DFT, regular DFA, density functional approximation, will be pretty bad because the gap is too small. LOSC give you very good approximation, and it's not so much dependent on which functional you use. Same story for many molecules. We have the same story for many molecules. I'll go very quickly and the result is similar or better than GW. So the quasi-particle energy quality is better or similar to GW. So that means the orbital, occupied orbital, is the ionization energy to excited states, and unoccupied orbital, then we can approximate the energy to the n+1, to the added electron state. Then that's give us another avenue or approach to calculate excited state energy. So excited state energy, suppose we want to know excited state energy of this excitation. Okay, this is the energy we want to know. We'll do a calculation start from n-1 ground state, n-1. Then the ground state n will be the LUMO. The LUMO will give you the ground state n, and then above LUMO will give you excited state of n. So the difference between these two will be the excitation energy for n. So all the information is obtained from the ground state calculation of n-1. And we call this method called QE, quasi-particle energy from DFT calculation for excitation. So this is the, I would say that this is the simplest way to calculate excited state energy. You just do a ground state calculation from n-1. And how good they are? They are, for the low-lying states, triplet and singlet, they are comparable to TDDFT. So this is the TD readout, TDDFT readout. This is LOSC. This is the DFA, just using regular density functional approximation. While we know the absolute orbital energy is not good, but the relative orbital energy difference, because this is low-lying state, actually it's really good. The error is small. So this is many molecules that we're looking at the error. Okay. So the total error is 0.4. With LOSC, actually, the systematic error is not cancelling that well, so it's slightly bigger than the regular DFT for low-lying states. But comparable, the results are comparable to TD result, TDDFT results. So you don't need TDDFT to calculate excited state energy. You just do a good DFT calculation for N-1. You get lots of information about excited states. Okay. So this is for low-lying states. But for high-lying states, how about for Ripper states? Ripper states, you can go to, this is lithium atom up to 6p6s on the different states. So if you take BLIP, calculate N-1, then the higher state has very large error because delocalization error don't cancel out. But for LOSC, we have consistent behavior from very low state to higher state. For Ripper states, also about the error is about 0.3 eV, the same thing as the lowest state. And same thing for LOSC B3 LOSC LDA. So the conclusion is that the DFT eigenvalue once can be identified as quasiparticle energy, and it describes also excitations of the N system when you use N-1. So we also look at the charge transfer excited state. Charge transfer excited state is a very difficult situation for TDDFT. You have to use a special functional for charge transfer. You cannot use same functional for valence excitation and charge transfer. So the charge transfer has a 1/r dependence because the charge transfer and then the energy has a dependence in r distance. And this, what I'm going, and running out of time, I'm going to go quickly. The result is that we have about 0.4 eV error when you do LOSC calculation. And also, most importantly, it has a 1/r dependence in terms of excitation energy as function of the donor and acceptor. I'll skip this. We can also calculate the excited state energy surface. So you can take this energy, total energy of N from the N-1 plus the eigenvalue that you calculate. And then, so this is the excited state's energy for N-electron. And then we can optimize geometry and calculate the surface. So describe the excited state dynamics using this. And you can also describe conical intersection, the degeneracy between grounds and excited states. And this is really something that's not possible or mistake in TDDFT, huge mistake in TDDFT, but with QE-DFT, describe very beautiful conical intersection. And now we'll talk about the self-consistency. So how this self-consistency was a challenge. How do we use orbital, localized orbital to calculate the presented density matrix, and then you do the correction, but then the correction will change the localized orbital. So it was quite a struggle for us until 2000. We come up with solution how to do the proper self-consistent calculation. So in principle, the localized orbital should be updated. You should update it during the self-consistent cycle. But then the Hamiltonian, the functional derivative, would be very complicated because the depend on localized orbital change with respect to density matrix. And that would be really challenging. So what we decided was that, during the self-consistent cycle, we can freeze the localized orbital. We don't change localized orbital. Just start your ground state calculation with a density functional, whatever version, GGA. You do a localization and use the localized orbital in the loss calculation, unchanged, fix it. then once you use that frozen, then the self-consistency is trivial. You have exact Hamiltonian. Self-consistency is just like a regular self-consistency. But then you can use the resulting orbital you obtained to change the localization again to do this cycle again. But we find it, we don't need it at all. For all the cases we studied, we have never found the need. We can reiterate and it won't change. So basically the update, the second step update, we call the macro iteration, is not needed, but we can do it if we want it. But so in the default is that we just use frozen localized orbital. And that solved the problem that Yongwu asked me. So that, and then the self-consistent becomes just a regular self-consistent calculation. Very simple, with clean Hamiltonian. And that allows us to do very complicated system self-consistency. So this, a last example is a transfer system that self-consistency plays such a big role. So what is this system is a donor and acceptor molecule, and we calculate as a function of the distance between the donor and acceptor. Okay, so this is the molecule charge on the donor and the energy as function of the distance between the two molecules. This is the HOMO from calculate from IP calculate from HOMO and calculate from LUMO the EA. So the very interesting thing is that for DFA, you get the partial charge in this system. You separate. That's wrong because the separation in limit is neutral. So MP2 is neutral, and our self-consistent LOSC is neutral. Yeah. So that self-consistency is important and was possible only if with this clean self-consistency. And the energy also reflected. So the energy, if we don't do self-consistency, do post LOSC, just add it to the correction, then it's wrong. It's not good. But self-consistency, we get the right answer. So the charge is very important. And the orbital energy, this is the orbital energy calculated from the combined systems. And this is isolated donor. When you separate to infinity, you can have an isolated donor calculate orbital energy, right? And you can see that for a GW, this is GW or EV, eigenvalue self-consistent GW, this point, last separation and the isolate donor nearly agree. That means they align okay. The level, energy level align okay. But the DFT will be wrong because it's a don't charge transfer. And our LOSC is correct, the green one. But for the acceptor side, the story is more interesting. For DFT, it's wrong because it has the misalignment. For all the GW calculation, even the eigenvalue self-consistency, the large separation does not agree with the isolated acceptor. That's because the charge error is so large that this don't agree. This is misalignment, level misalignment. Only in the self-consistent LOSC, we are able to, at last distance, agree with the separate donor, separate acceptor. So this really tells you that GW as a approach to solve problem has its limitation. It depends on the DFT functional charge significantly. And if you don't have it right, GW cannot solve the problem. And the self-consistent LOSC can solve this problem and get eigenvalue also in good agreement with experiment. So other development. So we have developed the library for LOSC as an open source program now that connect to PyICF and Sci4 for molecules. And the development for bulk is underway. And the LOSC for plus BSE, LOSC is as good as GW or better than GW. So we can combine with BSE to calculate neutral excited states, beta-Salpeter equation, and get very good results. Describe well valence, Weber, and touch change for excitation. So that's another alternative approach to excited states. And we also can do multi-reference DFT with PPRPA. I'm not going to talk about the localized orbital. This orbital list, in particular the frontier orbital, has a very interesting way to describe chemical reactivity. And this was a paper published last year to use the orbital list to look at the chemical reactivity. Because the molecular orbital, frontier orbital for large system is completely localized. It's not useful anymore. But the localized version with frontier orbital list is very useful. And I will stop here. And thank you very much for your attention.
Thank you very much, Weitao. So let's take some questions. Maybe I can get started with our main interest, which is solid state physics community mainly. So our students are mostly from physics, I'm guessing. So, for example, you mentioned QE-DFT. You need this charged system calculations, right? So, what can you do for the infinite solid systems?
Yeah, that's a very good question. I do not have an answer. I have thought of this for a long time. Don't know how to do this calculation for bulk. This is the same thing. I have another method. We have developed another method we call PPRPA, particle-particle RPA. And it starts from, so this is calculate excited state. In this system, it starts from N-1. But the PPRPA start N-2. So we have beautiful results for finite systems. But to extend it to bulk systems, I'm stuck. I have thought of this for a long time and I do not have an answer. I think it's really interesting, but I don't know how I'm going to do it. I still do not know. Basically, one cannot model a charge system very well with periodical boundary condition. So this is, if you want to literally do this calculation for bulk, you would do a calculation with 1 electron less for the entirely solid, right? So that's really, we cannot do that calculation. You have to you can do 1 electron less, but that's in a periodical calculation is nothing. It's then you just compensate it, so it will be infinitesimal for each unit cell, right? So I do not have an answer. How is the ramification for bulk system? Yeah, do not.
But
this is
excluding the excitation case, then would you say that, for example, maximally localized binary functions might be combined with your method?
Yeah. So
yeah,
you can use binary function and then take a binary orbital away, but it's not the ground state. If you take a binary orbital, it's not the ground state of N-1. So it's a different story. So in here, this N-1 ground state is truly the ground state of N-1. If you take a binary orbital away, yes, you can do that calculation, but it's not the right thing.
Okay.
So I do not know. It is a very intriguing question. Yep.
Okay. Thank you. So are there any questions from students or the audience? Or maybe Young-woo, do you have any questions, or maybe in comparison with your
No, I have a question that in your donor acceptor level calculation is quite very interesting and really have enjoyed a lot. So one thing I'm very curious about those kind of force in your system.
Okay.
So when you have a charge transfer, there will be a net force, right? So the molecular atoms atom distance will change according to the charging states or distance between the donor and acceptor. So usually those kind of localized linear combination of natural orbitals involve all the orbitals. So if you compute pulse, actually usually it's very non-trivial because you involve the many non-local part. For example, if you want to do binarization or loading orthonormalization, all kinds of things, it's a plate term will be very becomes to be non-trivial. So did you also consider such a kind of relaxation?
This is a system when actually at infinity separation there's no charge. So that's the ground state. But the excited state is this is the excited state. Let me forget. So you have a donor acceptor, and then the ground state is neutral at last systems. But excited state, you can the electron from a donor that give to the acceptor, and that create a charge, and in the excited state. So the excited states at this energy will have a 1 over R dependence because there's charge, right? So this is a excited state interaction in the excited state energy phenomenon, and then the excitation energy, this two energy difference has a 1 over R behavior. And this is really hard to capture with TDDFT with lots of challenges. But we shown that mathematically that the LOSC can capture that. This QE-DFT, using the QE-DFT, using the excitation energy with 1 electron less, using orbital energy, it has 1 over R dependence.
I see. Okay.
I don't know what this is what you meant. Then do you also calculate forces if it's necessary?
The force. I see. No, actually, for the LOSC energy constant known, we still do not have force. We don't have force. We have the self-consistent calculation of energy and then density, but the force we are still developing. It's not trivial. We need more work.
I'm wondering because usually I'm also trying to calculate the force to have a non-local kind of orbiter, and you always involve the derivative of kernel or U in your formalism.
Correct. Yeah.
That's really very non-trivial.
Yeah. So the force is non-trivial, and it will take quite a bit of effort, but I believe it's doable. But
sure. Sure.
And in particular, we already simplified the problem. The localized orbital is coming from the fixed calculation. That simplified quite a lot.
So your self-consistency calculation gives a lot of simplification.
Indeed. Yeah. And that means the force should be simpler, but not simple, but still complicated, but doable.
But it's very surprising that such a simple result. It's amazing. Amazing.
That actually shows that the first part of your lectures that was based on your expressions, right? So probably it shows that your principles about the fractional charge and spin that you discussed in the first lecture actually is kind of a law of constraint for your approximations, right?
Correct.
So I guess explains the physics why we have very good results in the end. Right. Okay. Okay, so it seems that it's lunchtime in Korea, and you must be very tired. Actually, I'm kind of tired after dinner. So probably we should let you go.
Okay.
Then, yeah, if there is any questions from the audience, please send an email to Professor Yang or me. Then I will deliver the question to him. And also, let me briefly advertise the afternoon lectures. So, Professor Jae-Kwang Lee from Busan University will give a lecture about the ferroelectric first principle calculations. So, with that, let's thank our distinguished lecturer, Professor Weitao Yang. Okay, thank you very much, Weitao. So,
Thank you.
for the rest of the evening. So sorry to keep you late. So goodbye. Thank you.
Bye-bye.
Bye-bye.
Thank you.
Really,
Bye-bye.
really
Bye, everyone. Yeah.
wonderful lecture. Thank you.
Thank you.
Thank you very much. Yeah.
Thank you.
고맙습니다. 네, 점심 맛있게 드시고요. 그래서 네, 수고하셨습니다.